Hi, so, let's see. Can everyone hear me? So I'm Thomas Marge. I just started my PhD here, so I'm going to be presenting some research I did during my master's on integrated offshore wind farm design. So just as an overview, oftentimes when people are trying to figure out turbine layouts for wind farms, there are a number of factors that they consider. The biggest factor is obviously the wake interactions between the different turbines, because if turbines are closer to each other, you have a wake effect from the first turbine slowing down the air velocity by the time it reaches the second turbine, decreasing power output. But there are all these other factors that are often only considered heuristically. So for instance, the cost of running the cables between the turbines when you're optimizing the wind farm turbine location is only considered, if at all, by using a shortest spanning tree algorithm. And our goal was to actually integrate the optimization of the cable layout into the overall methodology of figuring out how the turbines should be placed. And kind of as a background, we were using a Barrow offshore wind farm as an underlying case study as we were doing this research. So as a background to how we actually model the wake, so Jensen came up with this wake modeling concept where you look at the turbine and you look at the diameter of the turbine and you kind of assume that there's this constant rate of expansion of the impact of the wake behind the turbine, and that the energy that's taken out of the turbine at the initial location is distributed evenly across the space where the wake impacts the turbine and the airflow behind the turbine. So there's this expansion of the wake, but the effect of the wake also becomes lesser and lesser as the wake effect is expanding. And then you use the sum of squares property to actually account for the decrease in wind velocity behind the turbine. This turns out to be a very, very poor representation if you're looking at one turbine in front of another turbine with a wind in a specific direction, and you're trying to predict the amount of power that's lost at a very specific point in time. So if you ask me right now, can you predict how much power this wind farm is outputting? It's a really poor representation, but on aggregate, it's thought to be a very good approximation. So what we ended up doing when we were building our model is we built a model that could incorporate up to 4 years of 10-minute wind data coming from different directions at different velocities, and use that to actually predict that given a specific turbine layout, what is the electrical output of the farm going to be on aggregate over the course of a year. And to do that, we had to break the data from these hundreds of thousands of observations into approximately 8,000 buckets, considering 200 different wind speeds and 400 different wind directions, so that we could actually feasibly run the model. Now, the 200 wind speed bins and 400 wind direction bins might seem fairly arbitrary, but you can actually look at, for each number of wind speed bins, a different stochastic variable. And the expectation is that as you increase the number of wind speed bins, the stochastic variable that's underlying the power output for that number of wind speed bins decreases in variance over time, and at some point converges to the actual annual power production of the plant. So basically, we were taking these variance approximations at different numbers of wind speed and wind direction bins and trying to make sure that with a 95% confidence interval, we were within plus or minus 1% of the actual production of the plant per year, given the specific layout of the turbine in that scenario. After that, though, the problem doesn't get any simpler, because in order to actually integrate this into a true cable layout optimization problem, you need to consider both periods of low energy production and periods of high energy production. Because if you just kind of have this average energy production curve, on aggregate, in periods of high energy production, the cables that you install might not be capable of handling the high capacity energy, so that if you don't break your actual optimization process into different energy production scenarios, you won't be accounting for the true production possibilities of your curve. So we use the k-means algorithm to kind of find these clustered subsets of energy production scenarios so that our model had a good representation of what the actual energy production was. So then we took a step back and we asked ourselves, what exactly are we doing? And we knew for a fact that we couldn't integrate into a mixed integer program an optimization technique where we were able to place the turbines in any location. So algorithms like swarm model outputs are able to kind of optimize turbine placement in any number of locations, and you can see these very bizarre, all the way to classical kind of placements of what the actual placement scheme of turbines might look like, but we knew that wasn't going to be the focus of our model. Instead, we said that if we were given a scheme, so if we kind of roughly knew where the turbines should be placed, could we then further optimize, given that layout scheme idea, where the turbines should be specifically placed to further refine the model that was kind of presented by these more abstract swarm model outputs. So our optimization occurred in 2 stages. We'd first select a number of very similar turbine layouts that we wanted to compare to each other, and we'd run Jensen's model on each of these to calculate the costs associated with the different turbine placement schemes. And then we'd use mixed feature programming to actually refine the different turbine layout placement schemes and kind of compare the optimal configuration for the cable layouts given the specific schemes of turbine placement that we were considering. And we were able to include just about every factor that you could possibly want to be included in this model in our mixed integer programming, including losses over cables, except for these non-standard ideas of where turbines could be placed. So a little bit of a preview. In the end, we're able to compare the actual implemented Barrow offshore wind farm layout to the optimized layout, and basically refine both the scaling of the layout as well as the cable selection and the electrical configuration of the layout. And you might ask, how are we able to do this if we're only considering finitely many instances of the specific layout? And the way that we were able to do it is we kind of abstracted and we understood what we expected different components of the objective function to look like. So for instance, we expected that the investment cost of the layout would be very well fit by a linear model. So there's this idea that we were able to make these finite observations of specific instances of turbine placement, but then abstract the continuous range of possible turbine placements that were available by understanding that the investment cost should be represented by a linear model. And also, we expected that the weight cost should be represented by some sort of exponential decay model. And in practice, and the reason why we thought this was an exponential decay model was understanding the interactions between the power curves that say, okay, if this wind is coming in at this velocity, this is the amount of power that's output, in combination with the way that the wake effect decreases if you spread turbines further and further apart. And in practice, both of these components of the objective function were very well modeled in exactly the way that we expected them to. So we were able to create these powerful economic curves where we understood this continuous space of layouts based on only discrete finite observations of this specific instance of the layout, this specific instance of the layout, and this specific instance of the layout. What was even more exciting is not only were we able to kind of abstract and understand the true continuous structure of the different layouts, but we were able to manipulate the objective function to think about possible scenarios without rerunning the model. So for instance, the surface concession cost, or the amount it costs to actually obtain the part of the ocean where you want to build your offshore wind farm, is invariant to the actual optimization of the model that's built on top of that layout. So by having these continuous functions that represented the the investment cost of different components of the model, we're able to then build and manipulate these continuous curves to represent different scenarios of surface concession cost and different scenarios of cost of power not served and those sorts of variables. So not only were we able to refine the layout based on very specific assumptions that we fed into the model, but we thought that our model was also suitable for if you were going into the negotiation process and trying to figure out, is this an investment we should make? Then you could kind of look at the worst case scenario, the best case scenario, and play out over time, this is what our economic curves look like if we build this farm under this scenario, and this is what our investment will look like if we're invested in this farm, and the scenario plays out with much lower energy costs than we initially anticipated. So in the end, we were able to bound that in the worst case scenario, our optimized layout performed 6 million euros better over the life of the plant than the initial model that the Barrow offshore wind farm implemented, which represented a cost savings of approximately 5% of the total cost of the plant. So our final conclusions. So we created a robust model that not only was able to compare these very specific different turbine layout schemes to each other and say, if we compare this configuration to this configuration, this is the optimal configuration. But we were able to create these powerful economic curves that allowed us to explore this continuous space of wind farm turbine spacing, even though we weren't able to observe every single part of the curve, with incredibly good error bounds. And it was furthermore very easy to incorporate costs associated with different parts of the objective function to these models without having to rerun the initial mixed integer programming optimization, which was very expensive. In the end, we had a couple of disadvantages too. Certain parts of the objective function, like cost of power not served, weren't as easily modeled, but we're hopeful that in the future, because this represents a relatively small component of the overall objective function, this won't have a huge impact on the optimal layouts and the understanding of the continuous spacing space. And finally, because we were only able to work with one case study, we want to understand if this is true for all turbine layout schemes or if this is only applicable to this one instance of this relatively smaller farm with the specific turbine layout schemes that we were considering. Thank you. Yeah.
Thank you, Thomas. Questions?
Hi. So one of your major sort of cost saves looks to be the effects from the wake that you showed in your histograms. Just out of interest, so the wake function that you showed, was there any other functions that you tried to model the wake, or could you say a little bit more about what that function is and how exactly it was modeling wake?
Yeah, absolutely. So Jensen's model is kind of the state-of-the-art strategy that is used for modeling the wake. But up until this point, either the model hasn't had rigorous statistical bounds placed on top of it, or people haven't tried to understand the underlying curves that make up the Jensen's model. So we were kind of the first group that went out there and said we expect the underlying model to be this exponential decay model. And it's because we looked very carefully at the general trend of not only the power curve, which is if you give me a wind velocity, I'll try to predict the amount of power that the turbine is going to predict. But when we were deciding what sort of fit we thought the model was going to have, we looked at the operative range that the majority of the wind was occurring in this power curve, and we realized that the part of the model that we were dealing with in the power curve, which was mostly the lower part of the curve, so the 1 megawatt production, the 1.5 megawatt production by the turbine, that it made sense for the overall trend of the general farm based on the heavy weighting to that part of the curve to be this exponential decay. So even though towards the end, the actual part of this power curve was not exponential in nature, the differences in energy production were so small at the top of the curve that we assumed that the predominant nature of the impact was going to be in the bottom of the curve, and it turned out to be correct.
Your pictures of the wind farm layouts look like the North Korean army on parade. Is there any sort of mileage in trying to put down the rotors in some sort of irregular pattern?
There definitely is, yeah. And that's kind of what the particle swarm algorithms and the genetic algorithms have been able to deliver. So what we hypothesize, and we haven't actually been able to demonstrate, is that the curves produced from this kind of very rigid model could also be produced for these irregular patterns. So even though we can't produce these irregular patterns ourselves with our algorithm, we could still very easily fine-tune these irregular patterns.
But presumably if the wind's coming in a particular direction, you've got everything lined up in rows, then you're going to get a really big diminution of the output.
Yeah, although a lot of times when people use the genetic algorithms and the particle swarm algorithms, they can't incorporate all of the Jensen's wind data into their model. So they assume that the wind is just coming from this one predominant direction, and that creates a lot of issues because even if you have an average wind direction, even small variations in the average wind direction create huge changes in the actual power output of the farm. So when the designers of Barrow actually put together the Barrow offshore wind farm layout, they calculated the average wind farm direction, they oriented it towards the average wind farm direction, whereas in reality there were kind of two dominant subdirections which weren't in perfect line with the actual wind farm direction. And it turned out that when we were able to rotate the farm in our fine-tuning of the algorithm, we were able to create much greater power output by understanding that no, the wind's not coming from a single direction, it's coming from multiple directions. It's important to weight these different scenarios.
Right, if there are no more questions, then let's thank Tom again.